Okay, so we are on chapter two. This is on rocks and minerals, although we're going to start talking about minerals first. And to talk about minerals, we have to do a quick review over some basic chemistry concepts. I'm going to try not to repeat your high school chemistry class and just kind of select some things I think that are more relevant to geology. And so the first concept is that of isotopes. This is when an atom has the same number of protons and a different number of neutrons. And then just for review, protons have positive charges, neutrons have neutral charges, and electrons, not mentioned here, have negative charges. And some examples of common isotopes and why geology would care is carbon 14. It has 6 protons and 8 neutrons. Um, there are different versions of carbon 14. There can also be carbon 13. Again, the number of neutrons is going to stay the same. But as it goes from yes, I'm just going to say, as it goes from carbon 14 to carbon 13, it's radioactive. And that's how we're able to use carbon 14 dating when we go and like see how old plant matter or like an old piece of cloth or something like that is in archaeology or in geology. Also, because of their radioactivity function, some of them can be used for nuclear energy, with the example here of uranium-235 being used in reactor fuel, but it's just the isotope uranium-235, not the different uranium isotopes that can be used for that. Um, the atoms will bond together to form minerals, and there are different ways they do that. The first one, and kind of easiest to understand, is ionic bonding. That is when the anion and the cation are electrically attracted to each other, and so they stick together. The anions have negative charges, the cations have positive charges. And the most common example for that is table salt, sodium chloride. So sodium is a positive charge, chlorine is a negative charge, so they attract. Um, us in geology, we call table salt halite. It's the mineral halite, and that's why it says halite here next to the NaCl. They can also bond with covalent bonding, which is where the atoms share the electrons. So the electron kind of floats around between the two, if you recall that. And here's a review of the periodic table. This is based on the atomic number. Um, and here we can kind of group them together by characteristics they have. The first column is the alkali metals. This one here is your halogens, and these are your inert gases because that last outer valence shell is completely full, so they don't bond. And so they bond together and they form a mineral. And how do we know if it's a mineral that they have formed? It has to meet these 5 criteria. So it has to be naturally occurring. So these man-made minerals don't really count. Has to be inorganic um, and a solid. And then here's where it gets more to the chemical aspect. So it has to have a definite chemical composition with a regular internal crystal structure. And that crystal structure is then displayed through physical properties in the rock. And so here's an example of table salt. It forms cubes. So the atoms, as they are attracted to each other, the sodium and the chloride, they form little cubes. And if you look at halite as it's I mean, it's going to go ahead and say growing. It's a precipitate, so you can actually get it forming in large chunks seasonally as things dry lake beds dry out and things like that. Um, it forms little cubes, and if you actually look at your table salt and go put it under a microscope, it's going to be little cubes. And so if you break it apart, you just break it into the smaller and smaller cubes, and that is because it has this cubic crystal structure. This is calcium carbonate. It's very similar to a cubic structure. It's rhombohedric, and that's just kind of like slanted cubes, if you can see that. This doesn't look like it's been broken. It looks like this is its natural growth state, where you can see how it's kind of formed into that crystalline structure. But if you were to take this larger piece and break it down, each little piece would pretty much make this same little rhombohedral shape. And then they give this example of diamond and graphite. So both diamond and graphite are carbons. They're just made of just carbon. And the difference between them is the structure of how the carbon atoms are bonded together. And I mean, they're very, very different. This one's very, very soft. They at once put it in pencils until they realized that wasn't so good for you. And diamonds are very, very hard. So, like, very opposite minerals, both with the same ingredients, just built differently with those ingredients. So how do we identify minerals? It really is not easy. There are over 4,000 minerals. And so we have these properties that we can look at. And then there are books and charts and stuff. And so after we look at these properties, we can go to this book or this chart and then determine what we're looking at. Nowadays, there's so much advanced technology to help us identify these things, though, that you can there's a lot of machinery that we can take advantage of to help us. But if we're just out in the field and we pick something up off the ground, we're using these properties and then referring to a chart. So here are these properties. Color, there are some minerals where color can help you out, but usually you're not supposed to use color to help identify minerals. And you can see that here where you have one mineral that's different colors. And that's just because you have very, very minor impurities in that crystalline structure, and those little impurities can change the color, but not change the mineral type. Hardness. So I mentioned the graphite and the diamond. Diamond is very, very hard. Graphite is not. It'd probably be, I imagine, somewhere maybe around gypsum, where you can scratch it with a fingernail. If you can scratch it with glass, if you can scratch it with a penny. So these are all different properties that we use. So diamonds can only be scratched by other diamonds, or if there is another mineral with a hardness of one, I'm sure there are, but I can't think of it off of my head. Only can be scratched by something of that same hardness. Cleavage is how it breaks, which comes back down to that crystal structure, like talking about the halite and breaking it into like smaller and smaller cubes. Um, one of these crystal faces, we call that a cleavage plane. So if you break it, like right here, if you break it, like you don't see the entire cube, you just see the one plane. So that's a crystal face or a cleavage plane. Luster is kind of how light reflects on it. This is a metallic luster here that's being exhibited. There are also like glassy luster and opaque. Let's see, density, how much water does it displace? There are actually some minerals that are quite light and can kind of float. There's rocks that can float, and some that are much more dense. And then crystal form, we already talked about that. Looking at the common minerals and that periodic table, we can kind of group minerals together based on their chemistry. The most common mineral type on the crust of the earth is going to be your silicate group. And so these have silicon and oxygen, and those are pretty much the ingredients that they bond together in all these different framework geometries. You get all these different types of rocks. And some common ones here are quartz and feldspar, micas, clays, granite, very common minerals. Non-silicates that can also be common. You have your carbonates. This is like your limestone. You have sulfates and sulfides, oxides, which includes iron and aluminum ores, and then some native elements. These are like your copper and gold, and the ones that, gold just is an element on the periodic table. It doesn't bond with anything. Then we're going to switch to rock. I think we'll take a break here and I'll do another recording for rock.